Mass spectrometry is an extremely powerful tool for identifying the structure of organic compounds. It seldom provides enough information to identify a compound with a relatively complicated structure all by itself, but it gives extremely useful information. Here are some key points. It will tell you the molecular weight of a compound. For more sophisticated instruments, it will tell you the molecular formula of that compound. It also provides direct information about the weights of fragments of molecules. And that's also extremely useful. So we can see how big a molecule is. We can see the weights of pieces that it breaks into. And with sophisticated instruments, we can actually tell a molecular composition. It's a very sensitive technique. And that's an understatement. You can use this technique with samples way too small to see. Unimaginably dilute solutions can be examined for their compositions using mass spectrometry. It does not depend on the use of light. Which sets it apart from the other instrumental techniques that we'll talk about. It is destructive. The sample that's actually looked at is consumed. And importantly, for some applications, it's worth noting that the actual examination by the instrument is done one molecule at a time, or more specifically, one ion at a time. And it needs to, of course, look at lots of ions and count them all up to get enough to actually provide data. But those observations are happening one at a time, which again distinguishes this technique from all the others we're going to talk about. Well, how would an instrument like this work? Sounds like magic, and it's close to magic. Pretty close, reaches beyond the bounds of believability. But here it is. In a machine which uses a mass spectrometer, there's an electron beam. These electrons are traveling very, very fast. A sample which we'll call M for molecule, is introduced into the electron beam. So right here, the electrons collide with molecules of the sample. Now, it seems pretty hard to believe, but what happens when you bombard molecules with an electron beam of high energy? So you create positive ions. You actually knock out an electron. That's a positive ion. And a dot is placed there because this is not like a carbocation. This is a molecule that's missing a single electron and therefore has a positive charge. A second part of that machine and those molecules that are now what we call molecular ions travel through here and they are separated. And analyzed and the analysis tells you the molecular weight. Which actually is a reading of the mass to charge ratio. But since the charge is +1, what we're reading is a mass divided by 1, which gives us a molecular weight. And if we are using a very sophisticated instrument, in addition to the molecular weight, it gives the actual molecular formula, the composition of each of the various types of atoms in the molecule. Very impressive. If this were all that were happening, it would be very useful. But it's not. In this portion of the spectrometer, where the molecular ion has been created, the molecular ion is literally vibrating itself to pieces. When that electron smashes into that molecule, it not only knocks out an electron to create a positive charge, but it provides so much kinetic energy that the vibrations that result often cause breakage of bonds. So this molecular ion will, let's say, lose A, to form a fragment, and perhaps break a different bond to lose something else, to make fragment 2. These are positively charged, and because the bonds have been broken to lose radicals, they are no longer radical cations. They are simply cations like carbocations. And a third, to make fragment 3. You get the point. A variety of bonds in the molecule may be broken as a result of that excess kinetic energy. And the weights of these fragments are also determined. They're measured simultaneously. So now what we know are the weights of smaller pieces of this molecule. And in fact, these may be fragmenting as well to give even smaller fragments. So eventually we're looking at small pieces of a molecule that we can probably identify what it is, at least make a very good guess. And in that way, like people sort out a puzzle, of a jigsaw puzzle, by looking at individual pieces and figuring out how they could have gone together, if we look at individual fragments, we may be able to figure out how they could have been tied together by bonds to make the actual structure. So, mass spectrometry tells you the molecular weight, it may tell you the actual molecular formula, and it tells you the weights of fragments. In addition, in a mass spectrum, it's important information to see the relative amounts of the fragments that are formed, as well as the relative amount of the molecular ion. So it's going to tell us what are called the relative abundance of the ions that are observed. And the largest one is set to be 100%. All others are given relative abundance in percent relative to the largest one, and this is defined as the base peak. So, we have molecular ions, we have fragments, we have relative abundance data, and we have the base peak is the biggest peak observed in the spectrum. Let's take a look at one. This mass spectrum is taken from a database that's on a server kept in Japan. Extremely useful. Goes by the acronym SDBS. And these organic spectra can be found on the web, and access is free. I highly recommend using this if you need spectra for organic compounds. They have many, many in there. This is a mass spectrum for a compound we call 2-butanone. The heaviest peak is at 71, 72. Is that 72? And this is the molecular ion. These are the weights of fragments. So this is 57. This is the base peak. It is 41, 42, 43. Other peaks are much smaller, but notice there's a 29. That's pretty easy to pick out. The vertical axis is relative intensity or relative abundance, with the base peaks being arbitrarily set at 100%, and all other abundances, relative amounts of ions, being set relative to the base peak. And these are the actual mass numbers that correspond to those peaks, which are shown on the horizontal axis. Remember, this is mass to charge formally, but Z equals 1 in the elementary application of mass spectrometry, so it's the masses of these fragments. And there is some rationality to how this actually happens. For example, to form the molecular ion, where do you think that electron is going to come from? Well, it's going to come from where there's the greatest abundance of electrons available for loss, and look at that. So we are going to say that one of those carbonyl electrons is lost, and that leaves a positive charge. The fragments we see to go from the molecular ion to this one is minus CH3, 15. And we can understand how that happens. If this bond is broken, to create a fragment where we're losing CH3 as a radical, the fragment we make permits a filled outer shell of all atoms. So the loss of this methyl group makes a lot of sense. We could say the same thing about the loss of an ethyl group. To form an ion that has all atoms with the filled outer shell. And this weight is 43. So breaking the bond adjacent to the carbonyl, losing an ethyl group or a methyl group, makes lots of sense because we form a structure that we've learned is especially stable for an ion because all atoms have a filled outer shell. And that makes an ion by loss of methyl that has a mass of 57, or an ion by loss of ethyl minus 29. And oh look, we see a little bit of 29, where the positive charge actually remained with the ethyl group. And so we'd see that ion as well. Which brings me to another point. Look at the pattern that we see. This will be unique for this exact structure. If using a single instrument, you take the mass spectrum of two different samples, and they give them not only the same molecular weight, but the same pattern of relative abundances, those two samples are the same structure. So it's a way of essentially using, like a fingerprint, the pattern of the mass spectrum to positively identify an exact structure if you have a mass spectrum of a known structure for comparison purposes. Very powerful. Let's quickly take a look at a couple other cases. Here's another molecule. Has the same molecular weight as the 2-butanone we just looked at. So the mass spectrum would give a molecular ion of 72. The same as 2-butanone. But now look, cleavage of this bond, you lose a propyl group, and you have this structure, which has a weight of 29. Cleavage on the other side, you lose a hydrogen atom, and you form a fragment that has a weight of 71. So wouldn't it be easy to distinguish this aldehyde, butanol, from the ketone, 2-butanone, even though they have exactly the same molecular weights, by looking at the fragments that they make and their fragmentation pattern? One last example. See how easy it would be to determine whether the carbonyl group of a ketone was at the 4th carbon over or the 3rd carbon over? The fragmentation adjacent to the carbonyl here would lose an ethyl group. On this side, would lose a 1, 2, 3, 4 butyl group. The fragmentation adjacent to the carbonyl here would lose a propyl group, and, hey, would also lose a propyl group. So the weights of the fragments of the molecular ions would be distinctly different. In this case, both fragmentations would give the molecular weight of a single fragment. In this case, there would be two different molecular weights, easy to predict, because this is an unsymmetrical ketone. Mass spectrometry, an extremely powerful tool for identifying organic structures.